Welcome, everyone. Thank you for joining us for today's webinar, Incorporating Hazard Protection into Building Design, presented by Travis Holland and Anae Ray Baker. Now, for today's webinar, I want to go over a few housekeeping items. First, we want to respond to your questions following this webinar, so please type those questions into the Q&A box in the Zoom control panel, and our presenters will respond to those questions. At the close of our webinar today, please provide feedback by responding to our survey, where you can provide recommendations for today's presentation and future webinar topics. We are excited to have Travis and Anae present today, so without further ado, I will turn the time over to Wayne Repick, who is the Global Director of Business Development and Marketing and Communications and the Key Account Program Director for BakerRisk, to make a few remarks.
Thank you, Naomi. Good afternoon, everybody. Good morning, good evening, wherever you are. It is wonderful to be back. This is an exciting webinar. Certainly for us, this is our 1-year anniversary, and it's our 4th in the ongoing series that we've been having every 4 months. As you know, we put on a webinar to all of Egypt, and we've had tremendous response, certainly to this one, as we have with all of them. So it's good to be here again. I think you're going to really enjoy this session. I do want to give our thanks, of course, starting with the ministry, certainly His Excellency Karim Badawi and First Undersecretary Ala El Batal, who has been very supportive of what we've been doing. They've recently, as you know, come on in July, and they are aware of what we do on an ongoing basis. They've both been very supportive of it. We appreciate that support. We look forward to continuing our relationship with the ministry. And of course, I must thank Wessam Sakar, also at the ministry, for her continued support of everything we do in getting the word out to her and her team. Thank you, Wessam. So as before, as we've always done, we have an extensive Q&A process. We cannot get to all the questions that you submit during the session. We do have somebody that will be answering them as they can. Previous to this even starting, today's webinar even starting, I think we've had over 60 questions submitted, technical questions. We expect many, many more during this session. What we will do, as we've done before, is within 2 weeks, we will get the questions and the answers sent back to you. To everybody who's registered, so you'll have the Q&A sent to you. That'll be available within 2 weeks. Immediately following this webinar, everybody will get sent the copy of the deck of the PowerPoint presentation, so you'll have that for immediate reference. We will also, within 2 weeks, be sending you a recording that you'll be able to reference and go back and view this webinar at your leisure. And then finally, along with the documents that we send within 2 weeks, anything that Anae and or Travis reference with regards to other resources, references, white papers, or things that they may suggest during the Q&A, during that document, we're going to go ahead and provide those to you as well. And then finally, I believe we're going to have some sort of a link put up on our website for this for reference, so you'll be able to catch things there. If you somehow get lost in all that, reach out. We will get you what you need. We're very big on industry sharing. That's why we're doing this, and we want to be as supportive as we can of you as a professional in your industry. With that, before I turn it over to Travis and Anae, I do want to reference or remind you, Travis was the one who spoke at the short course that we gave last December for the Capacity Building Program Wave 2. So a lot of you will remember him, and you're certainly well aware of him. Anae, you will come to know, also on our structures team. But somebody who you do know is Amr Hassan. So I want to mention that he is here with us. And go ahead and say hello, can you hear me?
Hi, everyone.
Very good. Amr will be giving a little bit of a brief recap at the end as well.
Yes.
Great. Thank you, So that, I think, covers all the housekeeping notes. We're looking forward to this. And I will go ahead and turn it over to Travis Holland. Travis?
Thank you, Wayne. Thank you all. It's a pleasure to be here with you today. As Wayne's already mentioned, me briefly introduce myself, and I will let Anae just say hello as well. I'm Travis Holland. I'm located in Texas, USA. I am the manager of our structures group here in San Antonio. And then I am joined by Anay on the phone as well. Anay?
Yes, thank you, Travis, and thank you everybody for being here and attending the webinar and interest in the topic. I'm the manager of operations for BakerRisk in Canada and in part of the protective structures group, working with Travis for last 15 years. Looking forward to the webinar.
Great. Thank you. As we get started here, we have quite a full agenda to walk through over the next hour. Just as an outline of where we're going, the focus of our presentation is really going to be looking at how to implement the results of a quantitative risk assessment when you are completing a building upgrade for a building. We will start by looking at hazard identification and then work our way all the way to the end of implementing the upgrade design. But before we discuss about this webinar topics, I do want to introduce you all to BakerRisk. I'll remind you about who BakerRisk is. At BakerRisk, we have a single mission that is to provide solutions to manage hazards and risk. Through a 100% employee-owned company, we've been completing this mission for over 40 years. At BakerRisk, we have over 200 employees who are committed to this mission, and we continue to expand this mission not only at our home base in North America, but now expanding around the world. Glad to be with you in Egypt, opening our offices there in 2023, and also in the UAE in 2024. When people ask me what BakerRisk does, an easier question to answer is who the people at BakerRisk are. We are very curious and inquisitive engineers and scientists. We really enjoy asking the question, why? That's foundational at our company, and that's why here at the bottom of this diagram, we have testing and research. The things that we do are based on answering questions in the field, in application, at our test facilities. You'll see the benefit or the outcome of several of these R&D and testing operations throughout our presentation. It's through that foundation that we're able to do things like this, industry knowledge share, offer consulting services to our customers, and then provide software and products that makes it more efficient and effective to manage hazards and risk. We provide our services in 4 key areas: process safety, structures, blast, and incident investigation. The industries that we serve range from manufacturing to agriculture, to LNG, to oil refining. Industries that have exposure, handle or manufacture flammable, toxic, or otherwise hazardous materials. These are the industries that we want to help in managing their hazards and risk. Moving into the content of the presentation, Anay and I wanted to get things started off with a handful of videos to demonstrate the key areas of our topic, namely what is blast resistance and what impacts blast resistance. So to do that, the first thing I want to do is I want to share a video with you. This is a video of a test completed at the BakerRisk test facility located in Texas. This test facility is called our deflagration load generator. The deflagration load generator is the steel box you see on the screen. That is where our blast load is going to come from. The test object is a wood building. I'm going to run the video and then we can have some brief findings afterwards. This is a great video just to start with because the outcome is so extreme. But what are our key takeaway? Our key takeaway is that blast loads can cause significant building damage. Before I let Anae show the next video, I also want to point out a different finding from this. There's actually two buildings in this screen. The first one was this light wood building, and the second one was a reinforced concrete building towards the back of the test pad. So a second takeaway, which isn't immediately obvious, is that building damage also depends on type of construction. You will receive different levels of damage from a same blast load for two different types of construction. Okay, Anae?
Thank you, Travis. As Travis mentioned, in the videos, the purpose of videos is really to demonstrate what the hazard does to the building and appreciate the response of the buildings. And so we can take lessons from it and use it in our analysis and assessment. So what you will see in this video is response. And if you could just play the video. You can see this is a different type of response than what Travis showed in the previous video, where we had a global movement of the building as opposed to a destruction of a portable building. One quick point about this, the reason we chose these videos specifically is portable buildings have quote unquote a global appeal. You can see these buildings on various sites across the world. So what you're seeing here is applicable to a wide range of sites, and there are different forms of portable buildings, even including in Egypt. So with that, we'll move on to next video, and we'll look at another aspect of building response in our next video.
This next video is actually two videos. This is taken inside. These are video cameras placed inside the buildings we just watched in the previous video. While the previous video highlighted the response of portable buildings and how the response depends on the type of construction, this video highlights why it's important to understand what happens not only outside the building, but inside the building as well. So this first video I'm going to play is of the interior of the red building, the building that slid in that video we just watched. So the response inside the building, quite a bit different than what it looked like on the outside. Interior debris hazards, people moving around inside the building due to the response. And then we have the video of the gray building that did not slide in the video showed previously. And you have to look quickly because there's not a lot of movement that happens in this video, but not a lot of interior movement inside the gray building. So again, what's our key takeaways from these quick 3 videos? Building damage depends on type of, building damage can be significant. Building damage depends on the type of construction, and just knowing the building damage itself is not enough. You have to know what happens inside the building.
So the key points and the takeaways, I will let Travis chime in based on his experience, which is a significant experience in the design realm and construction realm of this, is that hazards from explosions can be significant and can have significant consequences and different kinds of consequences. So damage to the building envelope, sliding of the building, movement of the building, and internal debris in the building. And that's why we showed the video to illustrate that some of those hazards or consequences may not be obvious. And these are essential to focus on upgrade and mitigation efforts. Once we know the mode of failure and the hazard, we can address the mitigation effectively and provide a cost-effective solution to mitigate the hazard or risk. And I will let Travis share some of his thoughts before we proceed to the next topic.
This last sub-bullet here is really what we want to drive to in this presentation is once we know how buildings respond and what's important when assessing building damage, how do you implement cost-effective solutions to address that damage or to address occupant vulnerability concerns? BakerRisk has been doing this type of work, upgrading buildings, like I said before, for over 40 years. So looking at existing buildings in place that were previously not designed for any hazard response type, whether it be blast, thermal, or toxic, and then making those buildings blast, thermal, or toxic resistant. I'm just going to walk through a handful of slides that demonstrate how easy these upgrades are to complete once you know what the weak elements are. And then depending on how severe the magnitude of the explosion is, how extreme some of the upgrades are to address those concerns. So this first image is just a concrete block building that has been slightly reinforced to increase its blast resistance. We've also looked at a similar building where the wall needed to be upgraded in place. So concrete columns were added to the exterior to strengthen that building. Moving up in levels of extreme upgrade, and in this case, not only the walls needed to be strengthened for this concrete block building, but the walls and roof needed to be strengthened to address the blast concern. In this image here, this was a dual upgrade. This is for both blast and toxic resilience, that a canopy building was constructed over the existing building. And this is actually a good place just to highlight that most of the time the buildings that we're upgrading are critical to the operations. So making sure that the operations within that building can continue or at least partially continue during the construction process is of utmost concern. That's why this cocoon building allowed operations to continue while the building was being upgraded. And then finally, again, demonstrating a building under construction, in this case, both the walls and the roof, again, being upgraded to address the explosion hazards. So we show these images of previous work that we've done. The time it takes to develop a design and the cost it requires to implement the design can be significant. So making sure the decisions that are made leading up to the implementation of the upgrade are well thought out and well reasoned is important. And those are the types of topics we want to address in this webinar. It all starts from square one, which is hazard identification. And I'll let Ane briefly walk us through that process.
Yeah, thank you, Travis. So as Travis mentioned, it all starts with hazard identification. And so I'll walk through this quickly. I think it's an important aspect of design is identifying the hazard and defining a design basis of what are you designing a building to or a retrofit to. And so what I will do is walk through this process quickly because it's not the main topic of this presentation, but it's good for engineers to be aware that you're designing for a certain hazard, typically in a petrochemical refinery. So in the next slide, you'll see the process from left to right in a typical siting study or risk analysis, which starts with a scenario selection, defining congestion confinement, release sources, modeling buildings, which is our main focus, and then finally the results. And although as structural engineers, we're focused on the design of building, it is very good to be aware of the hazard that you're designing to. So you're speaking, quote unquote, the same language as the process safety and HSE folks. And things do not get lost in translation. So moving on to the next slide, I'll get to the key points of why this is important. So it's important for the members of the project team to be aware of the hazards which form the design basis. It's important because it can serve as a good quality check. So for instance, if you're a structural engineering team, designing for an upgrade, and you're aware that you're designing an upgrade for a vapor cloud explosion versus a BLEVE versus a firebox. There could be other hazards such as runaway reactions, and it's good to document in your drawings, project documents, what the basis of the design is, because oftentimes, believe it or not, incorrect hazard could be identified, and because it's mentioned on the drawing, somebody in the HSE team may actually catch that error during the design phase. So this is an important check. So we're not working in our silos of process safety people, structural people, etc. We're working as a team. And again, the severity of the explosion that we're designing to depends on the hazard. And so the key parameters are what's the explosion energy, what's the standoff distance from the hazard, and nature of the hazard. And a brief description of those included in your structural documents could serve as a good quality check. And so with that, this is a good segue into the next topic, which is the blast load. And again, the main focus of this is explosion hazards, which start with the load, and the load could originate from many different sources. As I said, it could be a BLEVE, it could be a bursting pressure vessel, or the most common of them all is the vapor cloud explosion. So I will walk through a couple of examples quickly, and then that sets the stage for us to talk about building design in more depth. So typically, vapor cloud explosion is governed by the level of congestion, confinement, and most importantly, the fuel reactivity. And we typically categorize fuel reactivity into three categories in the Baker's Strelo tank method: low, medium, and high. And I will show you some examples in the following videos of what the difference is. So one of the most commonly found low reactivity fuels is methane or natural gas. And what you will see here is methane released in a congested area for the purposes of this test. And you'll see the explosion in the video. Now, I hope your audio was on, because the visual impact of explosion is really complemented by the audio, which gives you a sense of the magnitude of explosion. And that was low reactivity. Now we move to high reactivity, which is ethylene, it could be hydrogen, and other fuels. If you look at this video, and again, I hope the audio was your audio was on, and you could see that it's a much louder explosion. All things considered equal, just the reactivity of the fuel was different. So this gives you a sense of the blast hazard to which you're designing to. And with this, key takeaways for this is that the explosion pressure is going to decay with the distance. And you will see in this video, this is a slow motion video that will show you explosion originating at the source and slowly propagating forward. And you can see that fireball as part of the explosion, a wave. And in the next slide, what you will see is that the relationship between the distance and the pressure. So as you move away from the source, you expect the pressure to decay, which goes back to identifying hazards and documenting hazards that you're designing the building to. So that's a brief overview of explosions. And in the next slide, I'm gonna just have two takeaways, which is material reactivity and standoff distance are the two key metrics from a standpoint of a structural engineer in appreciating and understanding the explosion hazard for which you're designing a building to. So with that, I'm gonna hand over to Travis.
Yeah, thanks, Anay. Just to piggyback on a couple of points that Anay was mentioning, we now have the explosion hazards how to calculate them or what to consider. Now an important question is, how does explosion hazards impact the buildings that we're concerned with? This is a computational fluid dynamics model that just shows a blast wave propagating from a source and then applying on a building. Important takeaway is the blast loads are applied on all surfaces of the building, not just the front wall or not just the roof, but a pressure wave is applied to all surfaces of a building. Related to that, when a blast load is applied to all surfaces of the building, the walls that face the explosion source will sustain a reflected blast load. That blast load is at least 2 times greater than the load that will be experienced on the back wall, not facing the explosion source, typically called a side-on surface. So these, in addition to the takeaways that Anae mentioned on explosion severity, we also look at how are blast loads applied to the building, and remember that blast loads are applied to all surfaces of the building, and that walls that face the explosion source will see a higher blast pressure than the walls that do not face the explosion source. Moving away from identifying the hazard and now moving into building damage and occupant vulnerability, this is the portion while you're completing the hazard study of understanding what the consequence is of the explosion. We calculate consequence in terms of damage and occupant vulnerability. Before we define damage and occupant vulnerability, I want to briefly revisit the term pressure we introduced in the previous slides, and then introduce this term called impulse. All these terms are important as we prepare ourselves to develop an upgrade to a building that has or is expected to be damaged from a potential explosion source. So when we look at pressure of a blast wave, the pressure is typically assumed to have an instantaneous rise to a max pressure labeled P max and is applied for a short time. We typically measure the time in terms of milliseconds. Now, this next term called impulse is just the area under that pressure time triangle. So impulse equals 1/2 Pmax times the duration. Now I can plot this pressure and impulse for any given blast load on a graph that has pressure on the y-axis and impulse on the x-axis. Placing impulse on the x and pressure on the y, I can place a point on the PI curve. Now, for any event that you have at a facility, there could be a range of pressures and durations. Some events having lower pressure and longer duration. Some events having very low pressure and longer duration. This is an intentional plot of pressure and impulse pairs on a graph that, as it turns out, that a building will respond to different combinations of pressure and impulse with the same level of damage, as long as those pressure and impulse pairs fall along this curve of constant damage, or an ISO curve. This is an important principle because what this means is that for a very high pressure yet low impulse blast load, the same damage can be caused as will be caused by a very low pressure, high impulse event. This is sometimes counterintuitive that different pressures can cause the same level of damage, but the important variable is not just the pressure, but also understanding what the impulse of that blast load is. Now I can take this principle of constant curves of damage, and I can form what's called a building damage level curve, which is a combination of several ISO PI curves to define different levels of damage to a given building. So in the plot I'm showing here, I'm providing a low through a high level of damage to a given building. And with this plot, I can categorize for this specific building how it will respond to any combination of pressure and impulse, or how it will respond to any blast load that I calculate. Let's walk through that, though, in a couple of real examples to demonstrate how a plot like this can be valuable. I'm going to show two videos. These videos were completed again at the BakerRisk Box Canyon Test Facility located in Texas. This testing was funded by the Explosion Research Cooperative, which is a cooperative BakerRisk has been running for well over 20 years with companies who deal with similar hazards that we're showing right now. The first video I'm going to show is of a metal building. This metal building is a conventional metal building. It's not designed for blast resistance. The second video is of that same metal building, but tested at a higher blast pressure and higher blast load. First video, at least from the exterior of the building, we don't see a lot of damage to the structure. The second video, though, as I increase the blast load, I see significantly more damage to the building structure. Now, taking the building damage level curves we showed earlier and the test we just recently saw, test 1, which resulted in low building damage, the pressure impulse pair for that test would plot somewhere towards the bottom left-hand corner of my graph, low damage. My second test, which had a higher pressure and a higher impulse and resulted in higher building damage, would plot towards the top right-hand corner of my plot. Just an example of how a building damage level curve could be used, and also an example of how construction, the type of construction can vary. The damage to the same type of construction can vary with the magnitude of blast load. All right, now that we know how buildings respond to blast, we now want to know what is it that we're protecting inside the building. Just knowing how the building responds is not enough to transition from a consequence assessment to a building upgrade. Answering the question, what is being protected, is important. What you may be protecting is critical equipment. The first photograph on the left-hand side shows a motor control center that's been damaged after an accidental explosion inside a facility. And here you see the roof joist, or the roof framing members, have actually collapsed on top of the motor control units. What you may be protecting are personnel inside the building. The second image on the right shows an office space after an explosion. So while you can't see a lot of structural damage to the building, what you do see is the suspended ceiling tiles, HVAC ducts, etc., becoming dislodged and potentially impacting the people who are working in this space. So if we're trying to protect people, we now need to define this term called occupant vulnerability, which we define as the percent possibility that an individual is injured or becomes a fatality after an explosion. As we define that term, we now want to ask the question, what is it that drives occupant vulnerability? We revisit the BakerRisk deflagration load generator. Here in this test, you've noticed that the test specimen is moved farther away from the DLG rig. And we've placed essentially a semi-truck container in front of the DLG rig. Next to the semi container, you can see a person in blue with a hard hat. This person is not inside the trailer, but will be exposed to the same blast load as the trailer is. So let's watch this video. two things. Two things we want to take away from this. One, you could visibly see the damage to the trailer. The trailer's roof was partially peeled off, and you saw the overall racking of the trailer. The second thing is that the individual who was sitting next to the trailer appeared to have a very low response to that blast load. The person's hard hat was knocked off, but for the most part, the person, or the dummy in this case, stayed in place. So what's our takeaway? Humans in the open have a high tolerance against overpressure compared to building structures. Now let's demonstrate what happens inside that same structure. This is revisiting the same test again, but now I'm taking a look inside the building, inside the trailer. Inside that trailer, we've placed two dummies, one dummy in a seated position and the other in a standing position. This video that I'm going to show is taken from the inside of that trailer. The blast is going to come from the bottom left-hand corner of our screen and apply to the building where the person is seated, and then we have the person standing just off camera. A different level of response for the individuals. So are compared to the individual on the exterior of the building. So what's our takeaway here? The vulnerability of humans is higher when inside a building. And answering the question we started this discussion with, what drives occupant vulnerability in a blast event? What drives occupant vulnerability in a blast event is the building structure. It's the damage to the building structure or the contents of the building structure that drives vulnerability, not the blast wave itself. Now we can correlate this as we increase the levels of damage to the building. We would expect that there's an increase in levels of vulnerability. In fact, that is true, is that as we increase the building damage level from low levels of damage to higher levels of damage, the occupant vulnerability inside the building increases. Now, taking all the points that we talked about just briefly and summarizing them, we first introduced a pressure impulse curve that we can plot blast loads on to determine levels of building damage. We then introduced that for a given building damage level, there is an associated occupant vulnerability. And as we increase building damage level, we also anticipate that we're going to increase occupant vulnerability. And as we put all these pieces together, we can see that using pressure impulse curves and defining levels of vulnerability, I can define building damage level and occupant vulnerability for any given blast event for a given construction type. This is an important principle as we move into the next topic of risk, specifically explosion risk with an A.
Thanks, Travis. Before we talk about risk, one quick takeaway from what Travis presented. I know the audience here has a background in various specialties, but one key takeaway here is that when we hear that a building is blast resistant, it's important to understand what pressure the building was designed to, what impulse it was designed to, and what damage level. Because oftentimes from a practical standpoint, we get information from process safety teams where they say the building is blast resistant and it has 3 psi blast resistance. And our follow-up question would be, but what's the impulse it was designed to and damage level? So just wanted to mention that before I move to the risk assessment, which again is a topic of great interest to me because this really ties the structural aspect and the process safety aspect into a metric that we typically use to manage risk and mitigate risk. So what I'm going to focus on is building damage, but combined with frequency and how it eventually results in the main metric we do measure against, which is risk. So moving on to the calculation. So Travis has introduced the concept of pressure impulse diagram, which you can see here. And these different pressure impulse curves, also known as the PI curves, are essentially lines causing a similar damage. In this case, building damage, red curve being a curve that separates damage from heavy to collapse, and the other curves showing lesser and lesser damages. So in the next, yes, thank you. So in this graphic, you will see a few scenarios. So each dot of a blast load on that curve being a scenario, and each scenario has a pressure impulse and an associated frequency. So in this illustration, you will see a somewhat of a lower blast load in that scatter plot, but potentially with a high frequency because it's a low level of blast load causing a certain damage. Now you'll see these other points introduced in the scatter with a different level of load causing a different level of damage with medium level of frequency. And so each blast load will result in a damage, but also has a corresponding frequency. And that's where we start tying in what Travis has talked about in terms of building damage, and then the frequency aspect, which is typically calculated by process safety engineers and risk analysts. So moving on to the next scatter plot, which shows a point with a significantly higher blast load. As you can see, that point falls above and to the right of that red curve. So that blast load would predict a collapse of the building, and in this case has a high consequence as a result, but a low frequency. So although the consequence from that load may be high, the frequency is low. And so each scatter point in a nutshell represents a damage and a frequency. And as a result, occupant vulnerability and frequency. And those two things brought together is what we would call risk. And so in the next illustration, this is a really nice graphical illustration to show risk is cumulative. In other words, risk from each one of these dots gets added up, and the summation of each risk component gives you a cumulative or total risk to the building occupants. As illustrated here, it's consequence multiplied by frequency, where frequency comes typically from a risk analyst. And how this ties together at a big picture, you'll see in the next slide, is you can repeat this process across the sites where each building will have an individual risk and a societal risk. The BIR column, or the second column, is the individual risk column, which is typically independent of number of people in the building. And then the SBR column, or column number 3, is the societal building risk column, which is function of number of people in the building. And you can see across the site, when you do a risk analysis and calculate risk, this gives you a good basis to prioritize how you move forward with your capital projects for risk mitigation. So in this example, in the next illustration, you will see that the risk building with the highest risk contributors highlighted. And so that would be your logical starting point for risk mitigation. It helps your capital project teams to prioritize projects, budgets in a way that you can reduce risk in a defensible manner, but also in a quantitative manner. Travis, with his experience in capital projects and building upgrades, I'm going to let him talk about the process of risk mitigation from a practical construction standpoint. So I'll hand this over back to Travis.
Thank you, Anay. We spent some time going through this first portion or presentation, which was the hazard study, looking at hazard identification, blast hazards, consequences, and frequency. Some of this was background knowledge for this group, but this is very important before we move into mitigation to understand the building blocks of the mitigation. Why are we mitigating? What are we mitigating? And how will we know our mitigation works? And if we can't answer these questions, the the money we're spending is not worthwhile because we're not addressing the true hazards. So that foundational piece is important before we move into this final piece of the presentation, which is mitigation, incorporating the hazard into protecting your people or your assets on site. All right, so to do that, we're going to revisit a similar plot that we showed previously, but then work through a couple of examples of upgrading a building to demonstrate why looking at explosions is valuable from a risk perspective versus a consequence perspective. In this example, I have taken 3 blast loads that are applied to a given building. This highest blast load shown in green does have a low frequency associated with it. That's similar to what Anae introduced previously. But Anae also talked about how that load has a high consequence. The way I read this graph is that loads that plot above the red curve would cause building collapse. So I have a very high consequence at a low frequency. If I'm looking at this problem from a consequence perspective for a given building shown on the screen, in order to make the building okay, I have to address that highest consequence event. The challenge in this situation is that highest consequence event is significantly greater than the capacity of my as-is building. And so if I am going to make my building okay in comparison to that event, I have to significantly increase the capacity of my building. If I increase the capacity of my building by 2.5 times, shown graphically in my PI curve, I will no longer cause collapse in my building. You now see that green point falling below my upgraded red curve. But I still cause significant damage to that building. What would an upgrade like this look like? This can be done. The roof in this case perhaps was the driver of the damage. And so a solution that could be implemented is extending the wall structure to where a new roof can be placed over the existing roof, therefore protecting the roof from the blast. This is not necessarily an easy upgrade to implement. Whenever you're starting to do work at the roof, you do bring up the potential for overhead hazards. You bring in the potential of breaking the existing weather seal of the building at the roof level. So there's challenges here. It's worthwhile investigating what else can be done or how else can I solve this problem. So a way to solve the problem differently is instead of looking at the consequence to look at the risk. Now that green load had a very high consequence, but we mentioned earlier it had a low frequency. There are, at the bottom of my PI plot, a couple of loads that cause a lower consequence, but have a very frequent occurrence. And it could be that if I strengthen the building enough to where these don't cause a high consequence, that I can have an acceptable risk for my building. So I don't have to worry necessarily about this curve or about this green plot, which is a very low frequent load, a very low frequency load. I only need to concern myself with the high frequency events. So again, looking at a similar building, how can I make this building slightly stronger to address just these high frequency curves? Well, it turns out if I increase the building just marginally by placing reinforcement at the exterior walls, I can make the building strong enough to where I significantly reduce my explosion risk, but I don't necessarily address the highest consequence, lowest frequency load. Okay, I introduced quite a bit there. Just a brief recap, and we'll go through a couple more examples. Advantages of using risk when you're completing a building upgrade. Number one, budget. I demonstrated it graphically that when you're looking at risk, there's the opportunity to save construction dollars by addressing your risk instead of trying to address your highest consequence event. Number two, a measured rate of return. When you know the metric you're measuring against, that is risk, you can quantify the risk reduction relative to dollars spent. So like most operations, there is limited budget. So understanding where the dollars can be best spent for the biggest benefit is important. And then finally, project efficiency. What is our targets? Are we attempting to get into the ALARP region? Are we attempting to get into a owner or industry acceptable risk criteria? Or are we trying to achieve negligible risk? Each of these can be done efficiently when we're looking at a risk metric instead of a purely consequence metric. I showed a couple of examples in the previous slide, which was the end result of the upgrade. I now want to briefly walk through an example, which is the process of arriving at that upgrade. To do that, I've shown a very simple building. It's a concrete block building that may be typical of a guardhouse or a lab or an operator shelter inside of a facility. To complete a risk assessment upgrade, you need to look at multiple upgrade options. And in order to identify what the risk reduction and the cost is before selecting an upgrade to pursue. So in this case, I've shown 4 different upgrades, each upgrade with a different level of reinforcement. Upgrade 1 being the lightest upgrade, moving through upgrade 2, upgrade 3, upgrade 4 being the highest level of reinforcement. In the example, a hazard study has been completed and the societal risk calculated at this given building in the as-is condition exceeds the unacceptable threshold at 5 ETH and -3. This is a good candidate for looking at building upgrades and what we can do to lower the explosion risk at that building. Using the same hazard study, I can calculate using the principles we showed earlier, what the explosion risk is for the upgraded building, upgrade 1. I can also estimate the level of construction dollars required to upgrade that building. I walk through this process for each of the upgrades that I looked at, and what I should be seeing is a decrease in explosion risk with an increase in construction dollars. And at a certain point, my calculated risk falls below the green tolerance curve. And now additional upgrades reduce the risk even further. Let's pause for a second and just look at what some key findings are from a plot like this. The first key finding is that as I'm investing more dollars, I'm driving down the explosion risk. This is a good finding. Each dollar I spent reduces risk further. The second finding is there's a couple of upgrades that significantly, the risk for those upgrades is significantly lower than the lower bound tolerance level. And a good question to ask is, why would I develop an upgrade that exceeds my expectations? Well, you can look at this plot differently. The second way you can look at this plot is how many people can I place in that building and still achieve my acceptable risk criteria. So remember, societal building risk is a function of the people inside the building. As I place more people in the building, my risk goes up. In the as-is condition, in order to meet the risk criteria, I would have to reduce the occupants in the building to about 1% of what they are currently in order to meet the risk criteria. As I implement upgrades, that level of occupancy reduction would decrease up until the point for upgrade option 3, where I can actually start adding people to that building and still meet my risk criteria. This is where it becomes important, because in upgrade 4, I can actually double the occupancy in that building and still meet my risk criteria. Actually, if I'm looking at a holistic view for the entire site, I may want to start implementing or addressing more upgrades to that one building, because I can start putting people from other buildings into this protected building to address not just the risk at one building, but address the risk at multiple buildings. Again, we've presented quite a bit of the how the process works to you. I want to briefly review a handful of construction upgrade projects that BakerRisk has completed at buildings that are similar to the construction that you would encounter at your facilities. This is a control room that required both wall and roof upgrades. In addition to the walls and roof, we've also addressed the blast resistance of the doors to ensure that people after an explosion event have an egress point away from the building. The second image I'm going to show here is of an upgrade completed really to address window hazards. In this case, the capacity of the overall building was adequate, but the windows became the weak link of the building. And so a shield or a barrier was constructed to address the window hazard. The images I'm showing right now, the primary function of these upgrades is for blast hazards or for explosion risk. There are methods that we'll show earlier that can be introduced to also increase the thermal resistance of a building, but right now we're just focused on blast. Again, this is an example of a building that did not require upgrade throughout the building, but just at one exterior wall. This is a great image to highlight several of the principles we talked about in this presentation so far. Why is it that only one exterior wall requires upgrade in this example? We talked about previously the walls that face the explosion source have a higher blast load than the walls that do not face the explosion source. Cost effectiveness was able to be achieved by understanding that principle and focusing upgrades only on the wall that received the highest blast load. Now, as we have talked about a couple of examples of building upgrades, I want to let Ane introduce a couple of more principles that are important when moving from the hazard study into implementing solutions.
Yep, thank you, Travis. So this is our last topic of the presentation, and one thing I want to say, been at BakerRisk for 16 years, and I'm still excited to work at BakerRisk and in this field because we don't know what we don't know. And the next video will illustrate that we're constantly learning of new hazards, and as a result, in the process of figuring out new ways of addressing those hazards. So what you will see in this video is a blast-resistant building, the design of which we've been doing for some time now. By that, I mean designing the building envelope to resist blast loads. But we intuitively always knew that if you have a portable building not anchored to the ground, and if you hit it with a large high magnitude blast load, it will have a tendency to move. And what you can see in the video on the bottom left is exactly that response of an unanchored blast resistant building. And what's now, in the scale of the video, that may not seem significant, but for the blast load for which the building's designed or rated for, which is approximately 8 psi, this can move as much as 8 or 9 feet. That's a significant translation. So imagine if this building was placed on a site where you had a slope going the other side of the building. This building essentially would fall off a cliff. And this is not an unusual situation where you would see buildings sited close to uneven ground, where yes, you have a blast resistant building, but it would be a very hazardous location for that building. And this followed into a few research projects where we figured out a solution to anchor the building, which is why I go back to, we don't know what we don't know, and we're constantly learning new things. What you'll see on the right is what happens on the inside, which again is the most critical piece of blast safety, is how will the occupants fare in a building. Again, what's important here is this is a quote unquote blast resistant building. But again, was it safe? No, it wasn't safe. And so that's what we're constantly learning, which is exciting. What I'm going to go to next slide is, again, talk about thermal hazards, but again, introduce why we are talking about it. Blast resistant buildings, when they became popular, there was a tendency to site them very close to the hazard because they were blast resistant. And in doing so, you inadvertently started placing them close to fire hazards. So you've taken care of one hazard, and now you've introduced another hazard. And we started this test program 4 years ago to address that question. Okay, is a blast resistant building typical, safe for fire? We took the blast resistant building. On the left, you will see a screenshot where a propane jet fire hazard was applied on the exterior of the blast resistant building. And on the right, we see fire damage inside the building. So an external fire heated up the building envelope, ignited the insulation, the plywood inside, and caused a fire within minutes. And so although the blast risk was reduced, the siting of the building had introduced fire hazards. And so we need to be aware of all kinds of hazards: explosion, fire, and toxics. So we make sure that the overall cumulative risk is managed appropriately. And this is a good illustration of that. And in the next slide, what you'll see is some mitigation from a fire standpoint. Again, what's important here is that a mitigation that's suitable for blast may not be suitable for fire, and vice versa. In this case, this is a good measure for fire mitigation, where you could have a firewall between the building of interest and the fire hazard. And what the wall is doing is shielding the building from the fire, which typically would not work for a blast. A blast wave cannot be stopped with a wall. You could use the wall to mitigate against fragments that may come from blast, if that's applicable, but not the blast wave itself. But for the fire, a wall can be effective if properly designed with a CFD analysis. And so this is just wanted to illustrate the difference between mitigation options between different hazards. And with that, we get to our closing remarks, and I'll let Travis make some remarks and hand it back to Wayne and Naomi.
Great, thanks, Anae. Before we close here, it's been a pleasure being able to share with this group. When we started off the presentation, we introduced that BakerRisk has a passion for sharing our knowledge. There's several people behind the scenes at BakerRisk that you can't see here that spent countless hours completing the test programs that we've been able to share with you today. But it's been a pleasure sharing the learnings from those studies with this audience, and we hope that you have taken several of these key points and learning objectives away from the webinar. So the first of our key points was we want to understand the consequences associated with explosion hazards. And then we wanted to understand that what does consequence depend on? It depends on building construction, the magnitude of the blast load, all the things we talked about in the early slides of this webinar. And then as Anae has shown in a couple of these last slides, the consequences may not be immediately obvious. So understanding what the hazards are, how the building responds, and how people can be protected is essential to making sure you introduce a successful mitigation program. As we started this webinar, we wanted you to take away 3 key points. We wanted to focus on how you can use the QRA or risk assessment to develop focused upgrade solutions for your buildings. We wanted to introduce our experience in designing and constructing the required upgrade solutions. And we wanted to introduce this principle of utilizing the risk assessment to implement cost-effective solutions in addition to mitigation effective solutions. Again, it has been a pleasure talking with you all. At this point in our webinar, I'm going to open the floor with Naomi for questions.
Thank you, Travis. Wayne, I'm going to go ahead and let you and Amber make any remarks that you'd like before we go into questions. We can give people enough time.
Thank you. Thank you, Naomi. Thank you, Travis and Anae. As a reminder, I saw a few questions. We are recording this webinar, and you will be getting a copy of this along with much other material. And you'll get a copy of the deck immediately after this webinar. We'll be getting that out to all registrants. Before I go into some other remarks, I do want to introduce Amr Hassan, who many of you already know, and get a little bit of a recap from Amr.
Yes, yes. Thank you, Wayne. Thank you, Travis and Anae, for this really informative presentation. It's really helpful. I just want to recap mainly three, 4 points regarding the building blast. I understand, I know that there's many operating companies in Egypt are fairly old, more than 15, 20 years. And we all know and understand that the QRA revalidation every 5 years. So please make sure to include the building risk assessment in the QRA revalidation for the senior management to understand and know the level of risk for the occupied building. Second point is also when we do the building risk assessment regarding overpressure and blast evaluation, make sure the study evaluate both overpressure and impulse as well. The third point, which is very important, I want to emphasize is that there is not only one option to mitigate the risk for the building. I know the most easy, but the most expensive is to build relocation. But there is also some other options for building upgrade. So please explore and analyze all the potential risk reduction measures when you do some actions to mitigate the risk for the building. The last point, which is very important, when we do the building risk assessment, I know that today Travis and Anae concentrate on the blast and overpressure, but also you have and must include all type of hazard in the plan. So you have to include the blast overpressure, you have to include the thermal, all type of fires, as well as the toxic, because in some cases the risk from other type of other than the overpressure is way more than the overpressure. So in some cases the toxic is the dominating. So please include all type of hazard when you do your building risk assessment. This is the 4 point I want to communicate with all the team in Egypt, and thank you very much, Travis and Anae.
Thank you, Engineer Am. Very good recap. Appreciate that. We are hitting close to 100 questions between what we got before the registration during the registration period, and then again today. So we have a lot of questions, a lot of Q&A to answer. We've got a couple that we polled. We're going to do those in just a moment. Beforehand, I want to remind everybody we have a 5th webinar that will be coming up in March. We typically will take the topics that are of interest to you. So please send us in interested topics, ones that you are really wanting to learn more about. This one was not scheduled, but we had so many people asking for more information on structures, blast-resistant design, that we moved this up in the queue. That's why we had this one today. So if you have a specific interest, send me an email. Let us know what it is that you're interested in, and we'll look at seeing that for March. That'll be towards the end of March. And then finally, we will be again at Egypt's in February. So please stop by. We'll have a booth there again. Please come by and say hi. Let us know that you're seeing these webinars, you enjoy them, share with us some insights that you have, and just come by and say hello. We're always happy to meet new people. And I saw a lot of familiar names on this webinar as well, so it's always good to see you. Thank you. With that, Naomi, I'll let you handle the closing Q&A.
Perfect. Thank you all, and great presentation, Travis and Anae. So As I said, I'm going to go ahead and ask some of the questions that did come up during the presentation. And then as a reminder to attendees, if you haven't already done so, be sure that you're putting those in the Q&A box so we can get those addressed. So first question for Renee and Travis, can occupant vulnerability impacts at lower damage level in a blast event occur?
Thanks, Leo. I'll take this first one.
Okay.
Yeah, great question. We highlighted this with a couple of our videos, but it may not have come across extremely clear. Interior debris hazards, like we saw in the video that Ane showed of the building sliding, or through some of the photographs we showed of contents like ceiling tiles dislodging, can occur at low damage levels to a building. So just understanding the building damage is not adequate to assess occupant vulnerability. You also have to understand what happens inside the building to the contents, ceiling tiles, walls, furniture during the blast event to correctly capture the occupant vulnerability. So to answer Naomi's question again, yes, you can have vulnerability and sometimes significant vulnerability inside of a building, even when the building has a low level of structural damage.
Perfect. Thank you so much for that. The next question is it appropriate to use a generic building blast capacity models to predict building damage and occupant vulnerability for all buildings at a facility?
I can take that, and Travis can chime in with his thoughts, but we would typically recommend not to do that, as we've illustrated that buildings are different, they respond differently. And so the uniqueness of each building results in a unique damage that it would sustain for a particular blast load. And so our recommendation is to ensure that the building models used are specific to the construction type that's being considered in the analysis.
And to piggyback on that, while what Ane said is 100% true, another advantage is if you do use specific building models to model specific buildings, identifying mitigation measures is much easier. The mitigation measures that you're going to identify are specific to that building and not generic. We've demonstrated several times in the presentation how construction type matters. When using the correct building assessment model and not a generic assessment model, you can start identifying these solutions very quickly after the completion of the risk assessment study.
Great, thank you for that. So another question was, are heavy construction materials like reinforced concrete the preferred construction material for occupied buildings within an industrial facility?
Yeah, I'll take that question. The heavier construction materials like concrete have a higher blast resistance than lighter construction materials like lightweight steel. However, saying that concrete is preferred over lightweight materials is not a good statement. What we want to do is site buildings appropriately based on the hazards at the specific site location. So siting a building like a light steel structure may be appropriate as you move away from the hazards. If you were to construct a heavy reinforced concrete building away from the hazards, you could be spending more dollars than you need to. On the converse, or flip side, a lightweight structure would not be appropriate as you move closer and closer to the hazards. There you would prefer heavier construction like reinforced concrete. So the answer to your question, Naomi, again, is it depends. Understanding that construction materials respond differently is important, and siting buildings based with cost efficiency in mind is also important.
Excellent.
Well,
go ahead.
One quick point I would like to add to what Travis mentioned is also if a heavy structure fails, it also has higher vulnerability. So while it can be strong, its failure can have a higher consequence compared to a light structural component.
Gotcha. And y'all did show some examples throughout the presentation, so thank you for that. And it does
And I
look like
could add one other
yes.
thing to that. So this, everything that Travis and Anae just said kind of reinforces the whole concept of addressing all of this before you actually have a building in place, which gets back to the, doing it during design. It's a lot less expensive, among
Yes.
other things, to do it during a design stage. And oftentimes we are brought in to fix something as opposed to address it during a design stage. And we'll do both, but it's just something to keep in mind that the earlier you bring in the engineer, the consultant, the designer, usually the better off everything is.
Yep.
Thank you for that, Wayne. Go ahead.
No, I'm good.
Yeah, I want to add something because I have seen it before. It's very important, as Wayne said, during the design, of course, to avoid spending much more money, but also very important to put the scope correctly.
Yes.
Because I have seen some studies done in the right time, but with the wrong scope. So it's very important to make sure that you put the scope correctly, and there's no harm if you not a professional at this point. There's no harm to get somebody to help you to put the proper scope. It will really save a lot of money in the future.
And these are all great points, and being proactive is what I'm hearing in y'all's responses. So it does look like we've run out of time for the webinar, but I'm going to go ahead and ask one more question before we conclude, and then some more closing remarks. So Travis and Anae, can a single design provide protection from thermal and blast hazards, or does each need to be mitigated through individual design solutions?
I would, I guess, do this in two parts. For a brand new building design, it's possible to have one solution that solves both problems. But for a retrofit, this is definitely challenging. And Travis, you can chime in on that. But to design a retrofit that meets both explosion and fire will definitely be an uphill battle. And so it depends. And this goes back to what Emar said and Wayne. This goes back to design basis and introducing these at the right time in scoping and in developing in a design objective.
Awesome.
Perfect. Well, thank you all so much. And as Wayne mentioned, we've only covered a few of the questions that were asked, but to our attendees, if you do have additional questions, please type those in the Q&A box. Travis and Anae will answer those questions. And as mentioned before, we're going to send that out, post their responses via email, newsletter, LinkedIn, and to our BakerRisk website, which will also have the link to the recorded webinar, slides from the presentation, and the answered questions from our presenters today. So again, when this is completed, there's also going to be a survey that comes up at the end of the webinar where you can provide your feedback from today. But as Wayne also mentioned, we want to know subject matter for future webinars. We, again, just appreciate that feedback from you all and your suggestions as well. So thank you again, Travis, Anae, Wayne, Amber. Great job today. Any closing remarks from anyone, or just say goodbye?
Thank you, Naomi.
Thank you.
On behalf of Travis and Naomi in Houston, and Anae in Toronto, and Amr and myself in Cairo, it's been our pleasure. We will see you again in a few months on a webinar, but hopefully we'll see you at Egypt's in February as well. So thank you, everybody.
Thank you.
Thank you.
Thank you.
Bye.
Bye.